Last class we looked into concrete production process, and now we said that basically the concrete is produced because cement reacts with water and it hydrates and thereby bonds various inert material like aggregate. So, today we will look into hydration process of cement. So, general outline of the talk today would be, first we will look into general cement composition, physical and chemical processes involved in the process of hydration, and then looked into what is known as setting, and then structure of hydrated cement. So, let us look at cement composition. Now, we mentioned earlier, it was in the last module sometime, we said that cement is produced by burning calcium carbonate found in limestone or chalk and silica, alumina and iron oxide found in clay or shale at about 1400 degrees centigrade. So, we burn limestone with clay. Now, this material sinters and then partially fuse to form what is known as clinker. Clinker is cooled and ground to a fine powder, a little bit of gypsum is added in the process, and this results in what is known as ordinary Portland cement, OPC in short form we call it. Just for the sake of information, India is the second largest producer of cement after China at the moment, and we can look into the oxide composition of the cement. Now, you see, we burn limestone, and limestone is calcium carbonate. So, when you burn limestone, the calcium carbonate, the carbon dioxide from the limestone is liberated and therefore leaving calcium oxide. The clay and shale or whatever it is, it leaves silicon oxides, iron oxide, aluminum oxides. So, therefore, various oxides are left after burning and they form into solid solutions, and therefore, cement basically composed, it's consisting of, or it is composed of various inorganic oxides. Approximate composition limits of cement is calcium oxide generally in ordinary Portland cement OPC is 60 to 67%, SiO2 around 17 to 25, aluminum oxide 3 to 8, and iron oxide 0.5 to 6%. Magnesium oxide is restricted to 0.1 to 4. There will be sodium oxide and potassium oxides alkalis 0.2 to about 1.3, sulfur trioxide 1 to 3%. There is something else called loss on ignition, which actually is a measure of unburnt material which can burnt and formed into oxides. So, those are the additional things. So, this is the typical oxide composition in cement. Now, one point I would like to mention here before we go to the compound composition of cement. You see, burning of cement, essentially we are actually generating carbon dioxide. So, therefore, from environmental concern, cement produces carbon dioxide, it consumes a lot of fossil fuel. So, the two ways actually it generates carbon dioxide. First of all, carbonate, calcium carbonate, limestone generates carbon dioxide. Since we burn fossil fuel in heating up to 1400 degrees centigrade, we further actually generate carbon dioxide. So, from environmental point of view, cement is not really so green material. Therefore, cement should be used very judiciously. It is a material which gives us artificial stone, but it should be used very judicious in a judicious manner and consumed as optimally as possible to the least amount, because it has generated so much of carbon dioxide. Now, let us look at the compound composition. These oxides, they formed into solid solution I mentioned, and this solid solutions solid solution compounds are, this is one compound, tricalcium, 3 calcium oxide SiO2, tricalcium silicate as we call it. This is dicalcium silicate, tricalcium aluminate and tetracalcium aluminoferrite. So, these are the main compounds of cement. right. And in cement, in case of cement chemistry, we actually abbreviate, because we can't write this big thing all the time. So, instead of writing calcium oxide, we simply write C. Instead of writing silicon dioxide or SiO2, we write S. Instead of writing Al2O3, we write A, and instead of writing Fe2O3, we write F. So, therefore, this tricalcium silicate becomes C3S, dicalcium silicate becomes C2S, and tricalcium aluminate becomes C3A, and tetracalcium aluminoferrite becomes C4AF. So, this is the abbreviations normally used in cement chemistry, and that is, those are the compounds, those are forms are C3S, C2S, C3A and C4AF. They are the main compounds in cements, main compounds in cement, they are complexes, as you can see. This compound composition can be found out, it can determine from oxide compositions by a formula known as Boggs formula, Boggs equation. So, that tells you, supposing you know the oxide composition, what would be the composition of C3S, how much will be the C3S, how much will be the C2S, how much will be C3A and how much C4AF, that you can find out. And that is what if I do, then I get, okay, this is again showing the same tricalcium silicate, to remember it because this is long name, tricalcium silicate, dicalcium silicate, tricalcium aluminate, tetracalcium aluminofluoride. This has been repeated, so that this is clearly remembered, because that is the terminology one uses again and again in the context of concrete and cement. Right. Now, if I calculate the compound composition based on the Boggs formula that we mentioned, we find that C3A comes out to be about 10.8%. C3S comes out to be 54.1 and C2S comes out from 16.6 and C4AF comes out to be 9.1%, assuming calcium oxide is for OPC 60 to 67%, which was shown earlier, which was actually shown in one of those earlier slides. So, you can see that roughly about C3 is 54, that is the maximum percentage, C2S is about 17 and C4A is 9 and C3 is 11%. So, one can calculate out the oxide composition, from the oxide composition one can calculate the compound composition. Now, this reaction is exothermic, it generates heat, because as I mentioned earlier that you are actually producing cement. Cement is not a man made material, we are producing cement at the expense of energy. So, we consumed a lot of energy because we burn it up to 1400 degrees centigrade, and therefore, or about so and therefore, we actually lock up a lot of energy, and this energy it can dissipate by reacting with water. Chemical potential is raised, and this chemical potential again it can come back to a stable state by somewhat stable state, relatively stable state by reacting with water. So, therefore, the reaction is exothermic, produces heat, and if we see the relative heat produced by different compounds, we will see that C3S produces about 502 joules per gram. It should be and this is 120 calorie per gram. This should be joules per kg. This should be joules per kg. C2S produces 260, C3A produces 867, and C4AF produces 419. So, this is a relative heat of hydration, and this produces maximum heat of hydration. It generates maximum heat on reaction, whereas this generates least. This is the next, and so on, so forth. So, as we can presumably understand that possibly this will react faster than anyone else, and this will react at a slower rate because it generates less energy. It is not an explosion generates lot of energy. So, it is instantaneous, whereas where heat of hydration is slow or the reaction heat is relatively less. So, it will be slow, it will be a slow process. So, this reacts immediately, maybe the next thing to react is this, and the lastly this reacts. So, this takes a long time for C2S reaction to be complete. Right. So, this is the heat of hydration of pure compounds. If we do a schematic representation now of the formation and hydration of Portland cement, this is what we should see. We shall see that first thing is you have elements wise, if you look at it, we will have oxides, oxygen, silicon, calcium, aluminum and iron. So, we have these elements, components elements, oxygen, silicon, calcium, aluminum and Fe. components oxides, this combines into form oxides like calcium oxide, silicon oxides, aluminum oxides and iron oxides. This is ferric oxides, and then compounds, this combines to form this compound C3S, C2S, C3A and C4A. And when you add water to this forms what is known as CHS gel and lime, calcium hydroxide, slackered lime. We shall see this a little bit in more details. Now, these combinations can differ in different types of cements. You can have proportions of these ones would vary, and by varying these proportions we can actually get different types of cements. Again, we will discuss this in details, because I can control the proportions of oxides. Oxide composition of the cement can be controlled relatively, it can be controlled from the raw material mixing etc., and thereby the composition of the compound composition of the cement can be controlled. And we know the properties of each of them, like I mentioned that C3A possibly reacts before anything else reacts, because it has got highest heat of hydration. So, if I want to increase or reduce the rate of say heat of hydration, then possibly I will have to reduce down the C3A component or C3A compound in the cement. So, by manipulating the compound composition, I can get actually various types of cement, and then I can add some additives etc. So, Portland cements plus various types of cements I can get, and when it added with water, it gives me hydration products. One of the major compound is called calcium silicate hydrate gel, CSH gel, and also it produces lime to certain extent. We shall see this in detail in next few slides. So, let us see, this is what happens to cement when I add water. Physically what happens? If we see this physically addition of water, when I add water with cement, it will be in a plastic state, it would be not liquid, not solid, it is plastic, because solid has got definite shape, liquid flows on its own and attains the shape of the container itself. Now, a plastic does not really attain the shape of the container on its own, but you can make it to attain the shape of the container. So, it is plastics, if you apply some force, it will move or change its shape to attain the shape of the container. So, when you add to the powder like material as cement water to it, it forms into a plastic mix, and uniform mix would be plastic. So, addition of water makes it plastic and a workable paste, as we call it, workable paste. This paste, because of the reaction that is taking place, it tends to solidify. After all, the reaction consumes the water, so it tends to solidify. Now, this solidification process actually we call it sort of setting, So, it sets to become a solid. Now, initial period we call it as a dormant period, right, when it becomes from solid to it goes to from plastic state, it goes to a solid state, and this should be minimum 45 minutes for ordinary Portland cements specified by most of the code. So, we call it initial setting. Initial setting means from the plastic state it goes to a solid state, not fully solid, but reasonably in a solid form, after which you can't deform it further without compromising on its properties like strength etc., So, if you try to give it a new shape after this time, well, there will be some loss of its property. So, that is what we call as initial setting. So, you add water, the mix is plastic and it is workable, you can actually apply force and get it into the right kind of shape, and then it initially sets. This time minimum should be 45 minutes and we call this as dormant period. Now, you see how do we measure this? Now, there is the basics ideas of physics and chemistry that was not available during those days when it was started. So, some specific apparatus was designed, that is called Vickers apparatus, that has got a mold where actually you prepare a standard paste. The standard paste is prepared with standard amount of water, which we call standard consistency. So, this paste you prepare with some specific or standard amount of water which is related to standard consistency, and standard consistency is again determined by the same apparatus, whereby you prepare a paste and allow a needle, a 1 centimeter 10 millimeter dia needle to penetrate through it. When the penetration has reached a specific level, we say that it is standard consistency. Similarly, we use a fine needle 1 millimeter needle to find out initial set. When it pierces such that its depth of piercing from the bottom of the mold is 5 to 7 meter, or it is said to have an initial set. We define it in a specific manner. Well, since we are looking into number of materials, we can't go into the details of this test, but initial setting time and final setting time and standard consistency is determined by Vickers apparatus. At the moment, I would like to mention something called false set and flush set. Now, false set happens when you have added too much of gypsum into the system. So, that is called false set, so you can remix it again. If the gypsum quickly reacts with water forming a solid, so as if it has solidified, that is called false set. So, you can remix it, and that is not and you can get the right kind of setting. Okay. So, that is dormant period initial set, but after that it actually solidifies further, and it takes about 10 hours of 10 hours of time. The maximum specified is about 10 hours time, by which it should become fully solid, but it still does not gain strength, it is not hard enough. If you try to pull it or push it, it would actually break. So, that after that after setting it is hardening. Hardening means gaining strength. Setting means going from a plastic state to a solid state. In initial setting, it is in dormant state, dormant period, and then it becomes stiffened and becomes a non-workable paste. You can't work on it after the initial set. It sets further, becomes full solid, such that if you open up the side mold, it will not collapse. It has got its now definite shape, and if you open up, if you just expose its side faces of the concrete or cement paste, it will no longer collapse. So, it has become stiff enough. So, that is called final setting, and beyond that, of course, it becomes a rigid solid, it goes on gaining strength, and that process we call as hardening, right. So, this also final set also corresponds to the time at which peak temperature is attained, because heat of hydration is produced simultaneously, and peak temperature is attained during that period of time, right. So, that is what is initial and final setting time. Now, let us see chemically what happens. We have seen the physically it solidifies, and let us see physico-chemical changes in slightly in more detail. Now, if you look at this diagram, then we can see physico-chemical changes that is happening, right. So, we can the x axis it shows the amount, this y axis shows the amount, x axis shows the time. This is or age after just mixing the water. So, initially these are 30 minutes, then this is in hour, then this is in days. Now, the first product to form, because I said the C3A is the most reactive of all of the material, and C3A will react quickly to water unless it is controlled, and it will react and give you an impression of what is called flush set. That means, C3A reacts and stops, inhibits the reaction of all other material, that is called flush set, right. So, in order to control this setting process, we add some amount of gypsum. Gypsum is calcium sulphate, and this calcium sulphate has high affinity for C3A, that is tricalcium aluminate. Tricalcium aluminate and gypsum reacts, forming calcium sulfoaluminates. The name of this compound is called ettringite. The name of the compound is called ettringites, right. So, that is the first thing, that is the first thing that forms during the dormant period, right, and you can see the dormant period here. The cement structures particles are here as if floated in water, and during the dormant period some reaction takes place and sort of fiber like growth takes place. This is the phase where the setting is taking place, and these fibers they grow, and the solids, the water filled spaces here, the water filled, these are water filled spaces outside the solid, and they tend to become filled in with fiber like materials, and this water reacts. So, the volume occupied by water now gets filled in by solids, and gradually more and more solids are formed, and in a very long run you will have a structure like this, which will have large amount of solids with some pores which were originally occupied by some water and some other special pores. We will come to this in detail. So, this is how physical changes that takes place. So, this is the period, dormant period, this is the situation, setting which is taking place, that is final setting, and the hardening, this is the scenario, and then final, it will form after 90 days or so, you will have a firm solid structures. Now, this phase you can see that this is attringite, this is mentioned attringite here. So, initially attringite is formed during the dormant period. Now, this attringite formation essentially is required to control the setting. Attringite is formed because of tricalcium aluminate reacting with the gypsum which we add. If we do not add gypsum, tricalcium aluminate quickly will react with water and it will give you impression of flush set. So, that is why we add gypsum, and that controls the initial setting characteristics. Now, this gypsum forms the attringite which expands in volume, and more attringite formation that takes place from inside, it can burst out the coat that has formed on various materials, and further reaction of other material can proceed. Okay, the details of the mechanism at the moment we are not interested, but we understand that initially the gypsum will react with tricalcium aluminate, forming what is known as attringite, and this attringite then get converted into finally converted into monosulfate later on. Attringite gets converted into monosulfate later on, which you can see there is some amount of formation is some amount of the attringite concentration reduces, and instead the monosulfate concentration increasing. This is the monosulfate concentration. C4AF, which is another minor compound, is not so very important, but its products, hydration product starts forming after about 7 hours, or like about 1 or 2 after 7-8 hours, and so on and so forth. Now, the main compounds that gives the cementing property of cement are the CHS gel, calcium silicate hydrates, because tricalcium silicate and dicalcium silicate, they react with water forming calcium silicate hydrates, and lime. We will see this chemical reaction in detail a little bit later. Now, initially this reaction starts about 6-7, not after 2 hours, but really it starts after 5-6 hours, and it continues in this manner. Now, this silicate CHS, initially they are long fiber, then they are short fibers, because fiber structures are shown here, this short fibers, and these fibers, short fibers are the most stable and they remain there. Also, another product that is formed is calcium hydroxide. So, the amount goes on increasing, this amount increases of the lime and the calcium silicate hydrate fibers, short fibers, they go on increasing. Initially they are long fibers, then they are short fibers. Attringite, initially they increase, they get converted into what is called monosulfate, therefore their concentration reduces, monosulfate concentration increases. Tetracalcium aluminoferrite hydrates, which is a minor compound of very little consequence, it starts from formation from this time, and its concentration also increases. Main product CHS, its concentration increases and becomes very high, and you can see the porosity goes on reducing, because the original spore space, original spaces were filled in by the original space of water filled space, and they were therefore solids were less, and therefore a lot of pores, interstitial pores between the cement particles. This goes on decreasing because the water filled space are now occupied by solid products of hydration. So, this increases, this pore space reduces, right. So, we can go to the next slide to look into the reaction process. Actually, main chemical reaction C3S, it reacts with water. In cement chemistry, we abbreviate water as H. Calcium hydroxide therefore is abbreviated as calcium oxide and H2O, that is CH. So, CH stands for calcium hydroxide. So, when C3S, this is one of the major reaction, C3S reacts with water, it forms this is CHS gel, it is a gelatinous structures, the fibers that we have seen, it has got gelatinous structures and some amount of lime is produced. In fact, 100 grams of C3S would react with 24 grams, approximately 23 or 24 grams of water, forming about 75 grams of CHS gel, calcium silicate hydrates, and 49 grams of calcium hydroxide, slaked lime, which is called same compound, same composition as same compound as slaked lime. So, the lime is formed. If you see C2S reaction, C2S reacts with similar amount we have assumed, although not exactly same, we shall again discuss this. 100 grams reacts with 24, producing less amount of lime, it produces less amount of lime, but both produces CHS gel, whereas tricalcium aluminate do not produce this same CHS gel, but it produces calcium tricalcium aluminate hydrates, right. It has got different stages, initially some this H6 is one product, there are other products formed. Anyway, that details we need not look into, but that is the main reaction of cement with products of reaction with of cement with water, right. So, these are the two main cementing property giving product, right. Let us see which gives the maximum strength. If we look at it, the strength giving compounds are, this is age in days, and this is compressive strength given in megapascal. C3S, it shows very high early strength, in the initial ages C3S reacts and it has got CHS gel which has got the bonding property. Basically, it is like this, you see this, when cement reacts with water, it forms this gelatinous structure which has got enormous surface area, very large surface area, possibly 1000 times more than that of the cement itself, and the surface forces starts dominating this van der Waals kind of forces, bonds, they are established between the material there and this CHS gels. So, CHS gels are the one which has got very large surface area, can bond inert material such as stones or cement, stones or let us say sand, and that is how it gives the cementing property. Lime on the other hand is a non-sealing precipitate, it is sparingly soluble, it does not go into the solution so easily. So, it goes partially into solution, sparingly soluble, it remains as non-sealing precipitate in the pore structure of the cement paste, in the unoccupied space of the cement paste. So, CHS gel is the main strength giving compound in cement, and we know C3S produces high CHS in the beginning, therefore, it gives you the early strength. So, it is the C3S which gives me early strength, but later on you can see as the age increases this strength does not increase, this is nearly becoming flat. Whereas, if you look at C2S on the other hand, C2S initially the strength growth is not so much, but it tends to give you long term strength. C3 on the other hand contributes very little to the strength of the cement paste, and C4AF contributes still lesser, but it is a concern because it gives you a lot of heat of hydration, and we will also see that this reacts with sulphate. So, in a hardened state C3A if reacts with sulphate and forms a trangite which occupies more volume, can be a durability problem. We will discuss this somewhat later on in more details. So, this is the strength, we can see that C2S and C3 as the main strength giving compound. Now, if I look at this backscattered electron image of cement paste in concrete, this is how it would look. You see backscattered electron. So, therefore, from the places where electron does not come scatter back, they will look black. In a backscattered electron image, electron microscopy image, actually the black ones are the pores, the white ones are unhydrated phase. The reflection in a gray image, reflection in a gray image depends upon how much scattering. So, unhydrated phase gives, there are equations of physics etc., which tells us that unhydrated phase gives us white color. Gray color of this kind are the hydrated phase and the black ones are the pores. So, cement paste consists of some unhydrated always, I mean unless it is fully hydrated, which takes very long time, and it would also depend upon how much water you have added with respect to the cement, in other words with respect to water cement ratio. So, with respect to water cement ratio, if you add less water, of course, everything will not hydrate. So, we shall see that again in details, but there will be some unhydrated material, some hydrated product which all look grey, because they will have different compounds in them, but all look grey color, and pores are the blacks. So, it has got some unhydrated product, hydrated product which will have again different chemical composition, might have calcium silicate hydrate gels, lime, as well as tricalcium aluminate hydrate, tetracalcium aluminoferrite hydrates, and so on. So, those are the compositions, but all those solids of product of hydration, they look grey. Unhydrated cement, grey matters are the hydrated product, solid product of hydration, plus some pores, large pores, capillary pores as we call. So, if I do binary imaging, binary what is called I am separate out thresholding as it is called. So, what I do, all pores I keep black, rest all I make white. So, these are the kind of pore structure you can see in a binary image. So, the all blacks have been left just like black, all other colors grey and whites have been made white. So, unhydrated phase and the hydrated phase all look white here, and this is the pores. So, two dimensional picture of the pores, typical two dimensional picture of the pores in case of cement paste in concrete would look like this. So, they are all of irregular shapes and sizes and interconnected and things like that. It will depend upon, of course, the ratio of water to cement and degree of hydration, etc., etc., and 10 micron is the scale. So, that is what is a paste, cement paste. Now, people have tried to model this by various types of analytical experiments. People found the structure of the CHS, they are like fiber like gelatinous structure, and that has been established as early as 1950s by various people who studied through scanning electron microscopy those days. Also, people have studied through nitrogen adsorption techniques, the thickness of interstitial layers of thickness between gap between, let us say, interstitial layers and so on, and they found that it has got a gelatinous structures. And one of the models proposed, say Isai, is something like this. He feels there is a layer structure, and between the layers there is some space where you will have what he call as gel water, because it has got a gelatinous structure. So, therefore, between the layer structure you will have gelatinous gel water. So, gel pores exist between the layers. Then there are intercrystal water, there are different types, right, and also adsorbed at the layer surface there is adsorbed water, and this water do not have the density is equals to 1, they are different, in fact they are different density. So, you have gel water or adsorbed water or intercrystal water, that is what Isai gave a model. Similar models were given by other people, like this one given by Feldman and Schroeder, and he defines interparticle bond, different particles bond between them, then interlayer hydrated water defined by X, and then CHS sheets. So, this C stands for CHS sheets, this O are the physically adsorbed water, and in between you have got X, these ones are interlayer, between the layers you have interlayer hydrated water. So, this is another model. So, what we understand from this? Well, they are layered structure, it has got a gelatinous structure, the hydrates, solid hydrates, solid product of hydration. They have gelatinous structures, CHS gel, they have gelatinous structures, and they are layered structure, and between this layer or at that in the layers themselves there will be some amount of water, which we can call as some would be of course chemically combined water plus physically adsorbed water and some gel water between the layers, right, and there is a pores between these layers which we call as gel pores. Well, Power gives this kind of a model. He says that there are gels, the layered structure of gels, layered structure of the gels, layered structure of the gels, those long ones, and the spaces between them are capillary pores, which has been left by water filled space which has got evaporated. Initially you have cement and water, and this water filled space, some of it will get occupied by the hydrates, cement hydrates. After the hydration reaction, hydration product will occupy, some of it will be occupied by the hydration product, but some space will remain still vacant and the water will evaporate from them depending upon how much water you have added. If you add more water, then more such space will remain vacant, and this space is called capillary pores, because their sizes are larger and they are between the CHS gel structure. So, there is a gel structure, in between you have got capillary pores. These are capillary pores, these are capillary pores, and within this gel itself there are gel pores. Within the gel itself there will be gel pores. So, within the gel themselves will be gel pores, which are finer in size. So, that is the model given by Pawar. Okay. So, what we see, pores in cements are of the two types: gel pores, which are actually micropores. The sizes will range from 0.5 nanometer to about 100 nanometer, 0.5 nanometer to 100 nanometer. Then there are capillary pores, which I can call as mesopores, and their sizes will range from 5 nanometer to 5000 nanometer. Now, we shall see sometime later on that these pores are responsible for shrinkage and creep of concrete, whereas these pores, which are larger in size, are responsible for mechanical and durability properties of concrete, right. So, these are the sizes of the pores, two types of pores we have seen. In addition to this, if I add some air and training agent, some admixtures, which I mentioned earlier that I can add admixtures to the cement, they can lead to something called macropores due to air entrainment. Okay, we will not discuss this at the moment, and if you do not do compaction properly, then also there can be some large pores, macropores, due to poor compaction. But first two are definitely inherent to hydraulic cement binder paste or concrete system, right. Okay. So, we will see that again. Now, let us look to this pore a little bit in more details. I can find out how much water or we know it, how much water will remain chemically bound to various compounds of cement. People have done very long term experiments, something like 12-13 years, and they found that 1 gram of C3S consumes actually 0.23 grams of water. C2S 1 gram consumes 0.1996 gram of water, although roughly we take for everything as 23 or 24. Earlier one of the reactions I showed 24, but this was observed, and C3A consumes about 0.522 amount of water. C4AF on the other hand consumes about 0.109 grams of water. So, 1 gram of C3S consumes 0.23 grams of water, 1 gram of C2S consumes 0.196 gram of water, and 1 gram of C3 consumes 0.522 grams of water, and 1 gram of C4AF consumes 0.109 gram of water. And also I know how much percentages of this compound is present in ordinary Portland cement. They are 54% for C3S, C2S is about 17%, C3 is about 11%, C4AF is about 9%. So, I can find out 1 gram of cement will consume how many gram of water. Calculation, simple calculation, because law of mixture, nothing else. Based on that, we can show that 100 grams of cement needs about 23 gram of water. This has been acceptable, this has been accepted by various experts, and generally it is accepted by concrete technologists that about 100 grams of cement needs 23 grams of water. There can be some variation here and there, the cement percentages of the C2S, C3S can vary small, even in OPC there are little percentage variation. It is based on one experiment done. So, now on an average we take it for granted that 100 grams of cement needs about 23 grams of water for complete hydration over a very long period of time. So, you can look into those pores in more details. Now, we define something called degree of hydration. What is degree of hydration? Because we said that this reaction is not instantaneous and it takes very long time. If all compounds of cement reacts with water completely and forms hydration product, then we say the degree of hydration is 1. If it is less, say 100 grams of cement I take, and let us say all 100 grams have reacted with water, then I say degree of hydration is 1. If let us say only 50 grams have reacted and 50 has not reacted, then degree of hydration is 0.5. So, it is the ratio of the proportion ratio of the cement that has mass of the cement that has reacted to the original mass of the cement, that we call as degree of hydration, right. So, before hydration degree of hydration is 0 and during hydration of course degree of hydration is H, and then if I look into a diagram, see initially I had cement and water, a schematic diagram, right, cement and water, and this has got a volume, let us say VW, and this is the VC, volume of cement. Then after hydration what will happen? I will have some unhydrated cement that we have seen from the BSE images. You will have some solid product of hydration, and this is associated with some amount of porosity. This is associated with some amount of porosity, right, gel porosity. This is inherent. This is associated with some amount of porosity, gel porosity, and this pores are occupied by water, we call as gel water. In addition, we will have some amount of originally water filled space which will remain vacant or will be filled by water, we call this as capillary water, which has not been filled by the solid. But we shall also see that there is some amount of space which will remain empty capillary. Why? Because if you see that the volume occupied by the water and solid cement earlier and the volume occupied by the solid product of hydration after reaction, we will find that there is a solid, there is a slight reduction in the volume as far as this is concerned. This occupies slightly less volume than the volume of water and cement that has been consumed in producing this. So, therefore, there is some amount of empty capillary formation always takes place while cement reacts with water. So, this is schematically cement and water reacts to form some unhydrated cement, some solid products of hydration, some space that would be occupied by gel water, some will be occupied by capillary water, and there will be some empty capillaries. So, this total constitutes the capillaries, this total constitutes the hydrated product of hydrated cement or cement gel, total hydration products of cement or cement gel. This is inherent to this. If this is, whenever this is there, this will be there because gelatinous structure. Since it is gelatinous structure, it will have the interstitial pores and that would be occupied by water. We can do a little bit of calculation to find out what will be the possible volumes of all those ones, product of hydration. We said 100 grams of C3S react with 23 grams, not C3S, actually 100 grams of cement, 100 grams of cement reacts with 23 grams of water. Now, let us consider 1 gram of cement. Density of solid hydration products have been experimentally found to be 2.43 to 2.59 gram per cc. In grams per cc CGS unit, experimentally it has been observed the solid product of hydration that is formed has got a density of 2.43 to 2.59 grams per cc. So, one can assume average density is about 2.51 grams per cc. You have cement, its density in CGS system would be 3.15 grams per cc, density of water 1 gram per cc. So, you have 3.1 gram and 1 gram combined together in certain proportion, 100 grams of course reacts with 23 grams, resulting in a product which has got 2.5 grams per cc density of solid. So, 1.23 grams because 23 grams reacts with 1 gram of cement. So, if I consider 1 gram of cement, 1.23 grams of cement product of hydration, product of cement hydration would occupy 0.49 cc because 1.23 divided by 2.51 is 0.49 cc. 1.3 1 divided by 3.15, that is the volume occupied by the cement originally, plus this was the volume occupied by water because the density is 1 gram per cc. That will result in 55, that is this is equals to 0.55 cc and this is 0.49 cc. So, this difference is it is this 49 cc is a volume occupied by the solid product of hydration. The original volume of the cement plus water is 0.55. This volume remains as empty capillaries. This volume remains as empty capillaries. 0.06 cc remains as empty capillaries. But this 0.49 cc has got an inherent gel porosity of 28%. Characteristics porosity of the gel is 28%. This has been again determined from experiments, analytical chemical experiments, that gel has got a characteristics porosity of 28%. By various kind of adsorption techniques, people have found out that various kind of adsorption techniques and other analytical tests, people have found out that gel has got a characteristic porosity of 28%. So, whenever this 49.49 cc is there, it will have always 28% porosity involved in that, and by that calculation 0.49 divided by 0.72 minus 0.49, because 0.72 is the volume occupied by the solid, the total will occupy 0.49 divided by 0.72, that is 0.68 minus 0.49 gives you about 0.19 cc. So, volume of gel pore should be 0.19 cc. By simple calculations one can see that 0.19 cc of gel pores will always be there. So, you have 0.49 cc of gel solid in your earlier diagram, 0.19 cc of gel pores if you have taken 1 gram of cement. Now, supposing I take C grams of cement and take degree of hydration as H, my gel volume would be 0.49 Ch, solid gel volume, gel pores will be 0.19 Ch, and it follows therefore, I can find out the total porosity by subtracting the original volume minus the volume of unhydrated product minus the volume of solid volume of gel, volume of gel pores. What is the volume of capillary porosity? What is the volume of capillary pores? Divided by the original volume results in capillary porosity, and expression for capillary porosity is something like this. W by C, you can derive this easily, very easily, it is not a difficult task, because what we are doing, original volume is known, then volume of the gel, solid gel is known, volume of the gel pores is known, volume of unhydrated cement is known for a given degree of hydration. So, we can find out what is the rest of the volume, since the original volume minus this volume of gel pores, volume of gel solid, volume of unhydrated cement will give me the volume of the pores, capillary pores. So, I can find out the capillary porosity. So, Pc denotes capillary porosity and it is given by W by C minus 0.36 H, H is the degree of hydration, this is the volume occupied, is related to volume occupied by original cement and water, 1 divided by 0.3.15 is 0.317 and W by C water to cement ratio. Similarly, gel porosity is given by this formula 0.19 H divided by this, and total porosity is the sum total of this Pc plus Pg, which gives you 0.1936 minus 0.19. So, it gives you W by C minus 0.17 H divided by 0.317 plus W by C. So, this is capillary porosity, this is expression for gel porosity, this is the expression for total porosity. Right. Now, what is important out of this is that if you have higher water to cement ratio, capillary porosity will be more. Physically we have understood this because volume occupied by the water in the original water cement system would be high and which will not be filled in by hydration product. So, more the water with respect to the cement, more will be the capillary pores. Gel pores is a function of hydration, degree of hydration simply. So, more the degree of hydration, more will be gel pores, because it is associated with the product, solid product of hydration, the CHS gel. More the CHS gel, more will be the gel pores. It is inherent, it would be there. And total porosity again is a function of water cement ratio. So, higher water cement ratio, high will be your total porosity. This is same everywhere, 0.317 plus W by C. So, higher the water cement ratio, more will be the capillary porosity and more will be the total porosity. Higher the degree of hydration, this would be gel porosity would be more. But as I said, gel porosity do not really contribute to poor performance with reference to strength and durability. It is mainly the capillary porosity which governs the strength and also durability properties of cement based system, and right now we are looking at cement paste. we can extend this idea to concrete sometime later on. There is an interesting point here. Supposing I put P c equals to 0, capillary porosity is equals to 0, then I will get value of H max. H max, this cannot be negative, the total pores cannot be negative. So, this has to be, if I put this equals to 0, this term has to be 0, and for this term has to be 0, you can find out what is the H max. So, if you have water cement ratio less than 0.36, from this it follows that if you have water cement ratio less than 0.36, you can never have full degree of hydration, some unhydrated cement will remain. Okay. So, that is what it is, right. So, degree of hydration, right, changes with age, as we have defined, degree of hydration changes with age. So, as the age increases, degree of hydration increases, fraction of cement that is reacting increases, right. But in some cases, if the water cement ratio is less than 0.36, you can't get complete degree of hydration. In fact, the H max will be given by W by C divided by 0.36. W by C, for example, if the water cement ratio is 0.3, degree of hydration will be 0.3 divided by 0.36. Maximum degree of hydration attainable is 0.3 divided by 0.36. But this is no problem anyway, because unhydrated cement, if it is there in the system, it does not cause any harm to the concrete or cement paste in general, because strength of such system or performance of such system is not necessarily governed by the volume of hydration product. On the contrary, it is governed by the negative aspect, that is the pores, because the pores are the essential flaws in such system. So, if you have pores, they bring down the strength. So, if you reduce down the capillary porosity, strength would still increase irrespective of whether you have got unhydrated cement is the system or not. Unhydrated cement will act like inert particle in that case, very fine particle, and they will be bonded by the other hydrated particle. So, you will have a very sound particulate system bonded together with very little pores in the system. So, degree of hydration, even if we do not achieve 1, it is not a problem. Since capillary porosity dictates the strength and durability property of concrete, higher water cement ratio means high capillary porosity, which means lowering of strength and lowering of durability performance of concrete, because cement is the contributing, cement paste or hydrated cement product contributes to the capillary porosity in the concrete as well, in addition to something else. And this is true for all other cement based materials, hydraulic cement based materials. So, therefore, our motto always remains to reduce down the capillary porosity as much as possible to improve upon the strength and durability properties, right. So, that is why complete hydration is not required, not necessary, but if there are pores otherwise, that is you have got high porosity, high water cement ratio system where the pores are there, capillary pores are there, they are more the degree of hydration, it would actually ensure that the overall capillary porosity is reduced. So, degree of hydration is important to that extent in high water cement ratio system, but in low water cement ratio system it will never achieve full hydration. Below 0.36 water cement ratio it will never achieve full degree of hydration, but that is not a concern, that is not a major concern, because this is always a question that whether do I need if there are unhydrated cement particle, will it really be detrimental to the strength development of concrete or not. Well, in low water cement ratio system where the capillary porosities are less, it is not a problem. So, main concern is capillary porosity in case of cement paste, and this can be extendable to concrete also. So, if we summarize now, what we have looked? We have looked into chemical composition of cement, then we looked into hydration, how physically the hydration what are the physical changes that takes place in hydration, and how do you define certain things, physical from the physical consideration as well as somewhat from chemical consideration like setting, etc. But remember, this is very difficult to actually have a sharp chemical demarcation as far as setting and such things are concerned. Therefore, we define them somewhat arbitrarily with respect to Vickers tests. Then we have looked also into the structure, physical structure, how it changes, and chemically what happens, that is also we have looked into. Then we have looked into products, and we have identified in the product, the solid products are always there, but then there are pores in the systems, and these pores are responsible for various performance characteristics of cement paste and hence to concrete as well. I think that would conclude our discussion on cement and cement hydration. Right. Next class we will look into types of cement and other cementitious material. Thank you for hearing.